Okay, so we already know how to use the fracture criteria to evaluate the safety vector or in the fracture behavior for the brittle materials. Okay, and now we're gonna look at the ductile materials by the yielding criteria. Well, it's quite similar to the fracture criteria, but we modify its the limit of strength. Okay, so we still have the three methods to evaluate the failure of ductile materials under static loading. The first we call it maximum shearing stress, and the second is the distortion energy method, and the ductile Coulomb-Moore criteria. Okay, so from your materials mechanics course, right? So we already learned how to evaluate the stress state in three-dimensional states, okay? And the normal stress and strain with the Poisson ratio, okay? Right? So you must remember that the strain with the Poisson ratio and the Young's modulus and the principal stresses, right? So the limit is that the materials has to be isotropic, right? If this material is homogeneous and isotropic, we can define the strand equals to is in terms of the material's property, Young's modulus, and the Poisson ratio with principal stresses. Okay, with principal stresses. In this case, it's only under tension, right? It's under tension. Okay, it's under tension. Okay, so now let's discuss what is criteria of the maximum shear stress. Okay, what is the criteria of the maximum shear stress for ductile material? Okay, so when the tensile spacement under the tensile test, we already know the fracture surface will along the 45 degree, right? For the materials point of view, because of the close packed plan, right, which has the highest atom density, right? Therefore, the sleep process will occur along that plan, right? And that plan with the 45 degree, okay, with the 45 degree. So the stress and strain curve for the tensile test of the ductile materials, we're gonna find the yielding point, right? Well, it is different from the brittle, right? For the brittle, maybe you will fracture directly, right? And the Young's modulus of the brittle material is higher than that of the ductile material, right? And the toughness, right, of the brittle material is higher than that of the brittle material, right? Okay, so suppose this we just pick up the small element, okay, from this tensile spacement, infinitesimal element, and we look into its stress state, right? So it's under the tensile test, right? The tensile stress, okay? And when this small element rotated specific angle, okay, when it rotated a specific angle, okay, it will reach a maximum shear stress. It will reach the maximum shear stress with average normal stress. Okay, so suppose this small element is under a tensile test with the plane stress condition, the plane stress state. So we have the principal stress, right? Sigma 1 equals to the principal stress, the maximum stress, and sigma 2 equals to 0, right? So we can plot this Mohr circle. Okay, we plot the Moore circle. Okay, so if this stress state at this small element initially, it has the normal stress with the sigma, right? Sigma here, right? Sigma here, right? So when this element rotated the angle, the stress will reach the maximum normal stress, right? At this point. When this point, stress state rotated specific angle, you will reach the maximum normal stress. Also, it rotated in counterclockwise, you will reach the maximum shear stress, right? You will reach the maximum shear stress. Okay, so if this element reached the maximum shear stress, the average stress is coexisting, right? So this point is the average stress, which is the center of the Moore circle. Center of the Moore circle. And for this maximum shear stress criteria, we define the maximum shear stress equals to the yielding stress. The yielding stress. Okay. Sorry, we have to say the maximum shear stress equals to half of the yielding stress. Okay, because we define the diameter of the small circle is the yielding stress right here, right? Therefore, say the maximum shear stress equals to the half of the yielding stress. Okay, so based on the maximum shear stress. Okay. Okay, so let's look into the Moore circle in 3D state. Okay, 3D state. So we will discuss with the three different cases. Okay, so if you still remember what we learned from the Moore circle of the brittle materials, it's almost the same. Okay, it's almost the same. Okay, so we have the sigma A, right? I will gonna modify the sigma A to the sigma, the principal stress, sigma 3, right? It depends on the rule of thumb. We are defining sigma 1 greater than sigma 2 greater than sigma 3. Okay, so that's just focus on the principal stresses. Here is the sigma A and sigma B, and which is the plane which the z direction, the stress in z direction equals to 0. Okay. Okay, so in this case, the sigma A and sigma B are both negative, right? Therefore, we can plot three more circles. We can plot three more circles, right? So we have the right here. Okay. So where's the maximum shear stress? Right here, right? Right here. Here's the maximum shear stress. Okay. So here's the maximum shear stress right here. Okay, therefore we say the half of the sigma A, the half of the sigma A is smaller than half of the yielding stress. Therefore, the sigma A, the absolute value of sigma A, has to be smaller than the yielding stress, right? So this is the maximum shear stress, right? And this is the yielding stress. The limit somewhere should be here. Okay, we say the yielding stress should be here. as y. Okay. So for the second case, the sigma A, the maximum normal stress, the principal stress, whose sign convention are opposite. Still, the z direction of the stress state equals to 0 right here, right? And we still can plot 3 more circles. Okay. And in this case, the more circles, well, where's the maximum shear stress? Here, right? Right here. It's the maximum, or here, right? It's the maximum shear stress equals to the radius of the Mohr circle. And therefore, we can say the sigma B, where, right, is which has the higher stress value, minus sigma A divided by 2, has to be smaller than half of the yielding stress, right? You know what I'm saying? So this term has to be the maximum shear stress, maximum shear stress. Okay, for the third case is that the sigma A and sigma B are both positive, right? And still the sigma Z equals to 0, right? And we can find the maximum maximum shear stress here and here, right? Of course, we can figure out what is the in-plane maximum shear stress right here, right? However, this in-plane maximum shear stress is smaller than the overall maximum shear stress. Okay, so in this case, we say the sigma B, half of a sigma B has to be smaller than half of the yielding stress. Therefore, the sigma B smaller than the yielding stress. Okay. Okay, so we follow the rule of thumb of the mechanics. Sigma 1 has to be greater than sigma 2, has to be greater than sigma 3. Okay, this is the principal stress. Therefore, we can modify the simples of A, B to the 1, 2, 3, right? Therefore, the case 1, we have the sigma A here and sigma B here. And sigma Z equal to 0, right? Okay, so right now, we just modify the AB to the 1, 2, 3. However, we have to also follow the rule of thumb. Therefore, the sigma A, sigma 1, sigma 2, and sigma 3. Okay, 1, 2, 3. Okay, the same for the second case, sigma 1, sigma 2, and sigma 3. Right? And the sigma 1, sigma 2, and sigma 3. Okay, so we just change the symbol of AB to the 1, 2, 3. Okay, A, B, A, B to change it to 1, 2, 3, right? So always the maximum shear stress occur for the condition of the sigma 1 minus sigma 3, because we define the sigma 1 as the highest principal stress divided by 2 has to be smaller than half of the unit stress. Okay, therefore say the sigma 1 minus sigma 3 smaller than the sigma y. Okay. Okay, therefore we define the safety vector evaluated from the maximum shear stress criteria n equals to the yielding stress divided by sigma 1 minus sigma 3. And we can also plot the stress envelope of the maximum shear stress criteria, right? So we just modify the stress limits to yielding stress, sigma sy, 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 right? Sy, yielding stress, yielding stress, yielding stress, yielding stress. It's a hexagonal shape. Okay. And from this stress envelope, we can figure out the linear equation in the second quadrant and the fourth quadrant, right? It's similar to what we already learned from the previous course, right? We defined the linear relation equals to y equals to mx plus b, the intercept of the y-axis. Okay, and the slope equals to 1 because this the boundary limit of the stress sigma a and sigma b is the yielding stress, right? Therefore, the slope is equal to 1, and we replace y with sigma b, replace x with sigma a, and the intercept with the y-axis is the yielding stress, right? Okay, therefore we can define the stress condition in the second quadrant. Okay, sigma b minus sigma a has to be smaller than the sigma y. Okay, so every stress condition within this area in the second quadrant should be safe. Okay, should be safe. Okay, so the second method for the ductile material under static loading, we call a distortion energy method. Okay, so the distortion energy method defines the strain energy per unit volume. So what's this mean? That's mean the unit volume of the metal or of the material, how many energy or how many deformation energy can be observed per unit volume. So if you still remember the question that I asked for you is if we have two cars, one's made by Toyota and the other one's made by the Volvo. If these two cars hit collide with each other, which driver would be safe? Do you still remember this question that I asked maybe a few weeks ago? Well, there's no any absolute correct answer, but I will say for some metal which has the huge strain energy, that means either this frame, this structure, metal structure, is being crashed. However, this metal structure will absorb most of the deformation energy to protect the driver to be safe. Okay, so that's the idea. So the energy we can define by first is defined by the resilience. Okay, what's the resilience? That's the area under the stress and strain curve within yielding. Within yielding, therefore we define the yielding stress. We'll just calculate the area, basically just a triangle. Okay, not real triangle, but we just approximate as the triangle. Okay, and the total area under the stress and strain curve is called the toughness, right? It's called the toughness. Okay, the toughness. Okay, therefore can define the distortion energy per unit volume U equals to half of the stress times strain, right? For the resilience, okay, for the resilience. Okay, the area here. Okay, so we have this idea of the strain energy per unit volume. Okay, so suppose we have the element, 3D element, it's under multiple stresses. It can be torsion, compression, and the bending, buckling, whatever. Okay, no matter what, we can just briefly integrate it into the principal stresses. Okay, no matter what kind of the stress applied to this element, we just simply simplify into the principal stresses, sigma 1, sigma 2, and sigma 3. Okay. Okay, and then we can divide it. We can separate this triaxial stress state in two parts. First is called the hydrostatic component. Therefore, this element is subjected to the average stress. And the average stress equals to the sigma 1 plus sigma 2 plus sigma 3 divided by 3. Right? And the second part is called the distortional component. Distortional component. What's that mean? That means this component deform this material. Okay, deform this material. Okay, therefore we can just modify the stress state, the triaxial state in distortion component equals to sigma 1 minus the average stress, sigma 2 minus the average stress, and sigma 3 minus the average stress. So this component make this material deform. Okay, make this material deform. Okay, so let's look at this strain energy per unit volume, right? So we have the principal stresses corresponding to the strain, right? As I mentioned, if this material is homogeneous and isotropic, and we can define the strain, which is the function of the Young's modulus, the material's property, Young's modulus, and Poisson ratio, and the principal stresses, right? I think it's quite a basic idea of the materials mechanics. Okay, and then we can plug those strain to here, here, here. Okay, okay, we can rearrange this equation, just expand it. Okay, just calculate, expand it, we can get this result. Okay. So, and then we just replace those stress, sigma, the stress with the average stress. Okay. Okay, we just replace this stress. Okay, sigma 1, sigma 2, and sigma 3 with the average stress. Okay, so average stress, average stress, average stress. Okay, average stress. And the average stress equals to the sigma 1 plus sigma 2, the sigma 3 divided by 3. They'll plug in here. Right? Plug in here. And we'll get this equation. Okay, so this strain energy we call it hydrostatic distortion energy of the hydrostatic component. Okay, hydrostatic component. Right, the different formation will be like this. Well, it's the same, but just different formation. Okay. Okay, so what is the distortional component? We have the hydrostatic component. It was a distortional component equals to the energy, the total energy minus the hydrostatic component. Right? The total energy, total strain energy minus the hydrostatic component. Therefore, the UD, right? So you can plug in, you can use this equation, okay, minus this equation. Okay, right? Therefore, you will get this equation. And this is called the distortional component. Distortional component. Okay? And if we just take the tensor test into account, let's say the sigma 1 equals to the yielding stress, and the sigma 2 equal to sigma 3 equal to 0. Okay? If we only consider the tensor test, right? So 2 equal to 0, 0, 0, 0. Okay? And sigma 1 equals to yield stress. And the distortional component can be simplified, right? In this term. Okay, in this term. Okay. So we can simplify the distortional component as a function of the Poisson ratio, Young's modulus, and the yielding stress. Okay. And then we just substitute this term to replace with the distortional energy method here. Okay, so we'll get the we say the distortion energy method. Okay, let's keep going. Okay, and then we define this term. We define this term, right? This is what we get. Finally, what we get, right, from the previous slide, right? We got this is called distortion energy method. We define this term as sigma prime, which is what we know the von Mises stress. Okay, so von Mises stress, or some textbook will write as the sigma Vm like this. Okay, so how to define this distortion energy method? And we can say the distortion energy method simplify the element under triaxial stress. Okay, and then we can just simulate it. This element is under a tensor test corresponding to the triaxial stress. Okay, originally maybe this element is subjected to the 3D stresses, right? It's quite complicated, and then we just use the tensor test, the tensor stress, to evaluate the 3D stresses. Okay, we use this tensor test to evaluate the 3D stresses states. And this value is called the von Mises stress. So the von Mises stress is not a real stress, right? Von Mises stress is not a real stress. And this is the very important issues you have to remember, okay? The sigma prime is not a real stress. Even we call it stress. Okay, it's just the stress for the tensor simulating the 3D stress states. Okay. Okay, therefore say the sigma prime has to be smaller than the yielding stress. Okay. And if we okay, if we just return to the simple A, B, right? So the sigma 1 corresponding to the sigma A, right? Sigma 2 equals to 0, 0, sigma 3 corresponding to the sigma B, and right, sigma 3 corresponding to sigma B. Okay. So even for the two stress states, the involving stress sigma prime equals to the sigma A squared minus sigma A and sigma B plus sigma B squared, well, square root of this value. Okay. Okay, so we can plot the stress envelope of the distortion energy method. Okay, we can plot the stress envelope. Okay, it's ellipse shape. Okay, so this is the yielding stress, yielding stress, yielding stress, and yielding stress. Okay, so those stress envelope is from the experimental data. Okay, it's from the experimental data. Okay, so we can plot this stress envelope by the sigma A and sigma B. And this distortion energy method can also evaluate the safety vector equals to this yielding stress divided by the sigma prime, the von Mises stress. Right? Okay, it's quite simple. Right? It's quite simple. Okay, so the third method for the ductile materials under static loading is called the Coulomb-Moore ductile. Okay, so the previous when we discussed the brittle materials, right? The Coulomb-Moore, we define some materials property like the SUT, the ultimate tensile stress, and the SUC, the ultimate compressive stress, right? For the brittle. Why? Because there's no yielding point for brittle materials that we can only utilize the ultimate tensile stress and the ultimate compressive stress. But for the ductile material, it always yielding at specific stress or strain, right? Therefore, now we just modify the stress limit from the SUT to the yielding stress for tension, and the SC, the yielding stress for compression. Okay, we just modify the boundary. Then we'll say that just modify the stress limits, right? The yielding for tension, yielding for compression, yielding for compression, yielding for tension. Sorry, this is for yielding for tension. Okay. Okay, we still can utilize the similar approach to find the linear equation, right? In the second and the fourth quadrant, right? We can figure out what is the linear equation, right? Of the second and the first quadrant is. Okay, so I just skip those process. Okay, and then we define the Coulomb-Moore criteria is the sigma A over ST minus sigma B over SC equals to the inverse of the safety vector. Okay, and then we just change the simple AB to 1, 2, 3. So the sigma A corresponding to the sigma 1, the sigma B corresponding to the sigma 3. Okay, and this relation is representing the Coulomb-Moore criteria for ductile material. Okay, and for example, suppose there's a stress states in the quadrant 1. So the sigma 1 is positive, sigma 3 It's 0. Okay, and then we can simply define the safety vector equals to the ST, the yielding stress in tension, divided by the Vomet stress. Sorry, divided by the sigma 1. Sorry, sigma 1. Okay, so there's one example here. Suppose we have the aluminum element whose stress state is sigma x equals to 150, megapascal, sigma y is 30, tau xy is minus 80. So we can figure out what is the average stress, which is the center of the Mohr circle. And we can figure out what is the radius, right? The radius of the Mohr circle is. So we have the center, we have the radius, we can plot the Mohr circle, right? So after plotting the Mohr circle, the principal stress can be found, right? So we have the sigma 1 and sigma 3. Sigma 1 equals 190, sigma 3 equals to minus 10. That's compression. Okay, compression. Sigma 2 equals to 0. Okay, therefore for the maximum shear stress, or we can call it Tereska theory. Okay, the safety vector equals to the yielding stress divided by sigma 1 minus sigma 3, right? And then we just plug this yielding stress here divided by 200. We get a safety vector from the maximum shear stress, 1.55, and the safety vector from the distortion energy method equals to 1.588. Okay. However, for this distortion energy method, the first we have to figure out what is the Vomet stress is. Okay. So which one is conservative? Maximum shear or the distortion energy method? Distortion energy method, right? Because the safety vector is higher than that of the maximum shear. Okay. Okay, so what we learned from this course or the materials mechanics course, what these we only focus on the we call the general state of stress as presented by 6 components, right? We have the element, and we can cut through the specific angle. Okay, and we take out this element, and we use the equilibrium equation, right? To analyze the stress condition on this element. Okay. Okay. Also, we can cut this element in octahedral shape, but not this triangle shape. Okay, so we can just cut. Okay, we can just cut. Okay, we can cut the small 3D elements into the tetrahedral, right? And it's still under the 3 principal stresses. Okay, and for the previous case, we have the only one surface, right? One surface. However, for the octahedral stress, there are 8 octahedral plane or octahedral surface, and on each surface, it has the average stress, and we call it the octahedral stress. The octahedral stress. Okay, And these octahedral normal stress are normal to the octahedral surface and are equal to the average of the principal stress. Okay, therefore and the octahedral shear stress lie on the octahedral surface. Okay, therefore define the octahedral shear, right? Equals to this equation, which is corresponding to sigma 1, 2, and 3. Okay, so then now we can use the octahedral shear to evaluate the fail of the ductile material under static loading. Okay, so the theory is that the yielding begins when the octahedral shear stress in the stress element exits the octahedral shear stress in a tension test spaceman at yielding. Okay, so you think, well, it's quite a little bit similar idea as the distortion energy method, right? It's a little bit, some part of it is are similar. Okay, okay. So this is what we define as the octahedral shear, right? And then we use the tensor to define the tensor spaceman at yielding to define the octahedral failure theory. Okay, therefore say the sigma 1 equals to the yielding stress and sigma 2, 3 equals to 0, right? So it's 0, 0, 0, 0, right? What we get the octahedral shear equals to square root over 3 times the yielding stress, right? And then what we do, we can plug this term, right? I just change color, let's replace this term to here. And yeah, this equation which represents the octahedral shear stress failure. Sorry, octahedral shear stress failure theory. Why? Okay, so well, it depends on, because you are an engineer, you're a designer, so you can select which failure criteria as suitable for your product or for your machine. Okay, so suppose the this component is under the pure shear loading, and more circles shows that the sigma A equals to minus sigma B equals to tau, which is the shear stress, maximum shear stress, right? So this conditions that if this element is under the pure shear bending, pure shear loading, sorry. Okay, pure shear loading. So what's this process to predict whether this component is gonna fail or not? Okay, so first we plot the equation on the principal stress axis, give the load line for the pure shear, and the intercept of the pure shear load line with the failure curve indicates the shear strength has been reached, and each failure theory predicts shear strength to be some fraction of the normal strength. Okay, so what's this mean? Okay, so let's look into this stress envelope. This is a stress envelope. Okay, for this maximum shear stress. Okay, the intersecting pure shear loading line with the failure line results in, this is the shear yielding stress. S means the shear, Y means the yielding occur. Okay, SY defines the yielding stress. Why? Because we have this distortional, you can look at the different stress envelope from the different theory. Okay, so it's the ellipse shape defines the distortion energy method, right? The hexagonal shape defined by the maximum shear, the dot line. Okay, the dot line. Okay, and for the pure shear line defines the sigma A equals to minus sigma B equals to shear stress. Therefore, this line is defines the pure shear. Okay, this line defines the pure shear. Right, this is a loading line, pure shear loading line. Okay, so and then there's an intercept with the maximum shear stress intercept right here. And there's the other intercept with the distortion energy method right here. Right? Okay, and then we can plot we can project the point to the sigma A axis. And then we find the point on the sigma A axis. Okay, and this point is the yielding stress, right? So we compare with this the distance between the project point to the yielding point. Okay, therefore we'll say this project point equals to the 0.5 yielding stress. Okay, yielding stress. And the intercept of the pure shear loading line with the failure curve indicate the shear stress has been reached. That means when this loading line, okay, so when this loading line reach the intercept of the stress envelope, this and this, that means the shear stress has been reached. Okay. Okay. So for the distortion energy method, the DE method, which is the shape of the ellipse, the intercept of the pure loading line, failure curve, right? So you can still use the same method. So for the we have the intercept that with the ellipse shape right here, right? Okay, and then we can plot this projection line with the sigma A axis. Okay, and the ratio between this length and this length. So this point will equal to 0.577. Okay, 0.577. So we say the shear yielding stress equals to 0.577 yielding stress. Okay. Okay, so summary for the ductile materials, the material shear is conservative, overused for the design. We have the high reliability. Okay, it's higher. Well, this result is consistent with what we calculated, right? From this example, forgot where. Oh, here. So for the maximum shear, which has the higher, has the smaller safety factor, it's more conservative. Okay, much more conservative. Okay, and the distortion energy matter is typical, often used for the analysis. We agree with the experimental data design, right? So this method, distortion energy matter, is close to the experimental data. Okay, and if the tensile and the compressive strengths differ, and use the ductile coolant more. Okay, and for the brittle materials, the Moore theory is the best. However, it is difficult to use. And the brittle coolant more is conservative. And in the fourth quadrant, and the modified more is still slightly uh wow conservative in the fourth quadrant. Okay. Okay, so I'm gonna stop here. So next chapter I'm gonna introduce for the failure criteria under cyclic loading. So that's mean the fatigue. Okay, that's mean the fatigue. Okay. Okay, so okay, so the course will be ended here.